Gram-negative bacteremia is a fast-moving, life-threatening infection. To stop it, clinicians rely on gentamicin, a powerful antibiotic with a notoriously narrow therapeutic window. If you miscalculate how quickly a patient's body clears this drug, you push them into one of two dangerous extremes: lethal toxicity or catastrophic treatment failure. Consider a hospitalized patient who receives a standard starting dose, a 160 mg IV bolus of gentamicin. After administration, we draw two serum drug concentrations. At hour 1, the concentration is 8 mg per liter. At hour 6, it drops to 2 mg per liter. To understand exactly how this drug is behaving in this specific patient, we need to calculate the elimination rate constant, represented as Ke. Ke is the mathematical representation of the patient's biological clock. It dictates the entire dosing schedule required to keep them safe. When faced with two concentration data points, the most common mathematical trap is to treat the drop like simple subtraction. It is tempting to assume that the body clears a constant, absolute amount of the drug every single hour. This chart shows concentration on the y-axis and time on the x-axis. If we subtract 2 from 8, we get a drop of 6 milligrams per liter over a 5-hour period. That creates a straight slope of 1.2 milligrams per liter disappearing every hour. This is the zero-order assumption. Zero-order kinetics means a fixed amount of drug is eliminated per unit of time, completely independent of how much drug is actually in the body. If you extend this straight line, it predicts the drug concentration will hit zero far too early. Acting on this prediction would prompt a clinician to administer the next dose prematurely, stacking the drug and causing severe renal damage. Human physiology does not clear gentamicin in a straight line. Relying on standard algebraic slope formulas here guarantees an incorrect model of the patient's kinetics. To accurately calculate the dosing interval, we must apply the correct model: first-order elimination kinetics. Under first-order kinetics, the body clears a constant fraction or percentage of the drug per unit of time, not a constant absolute amount. This chart reveals true drug behavior, an exponential decay curve between our data points. Initially, high concentration causes a steep drop. As concentration falls, the curve flattens. Mathematically, you cannot extract a constant elimination rate, RKE, from a constantly shifting slope. We need a specific mathematical tool that can take this changing exponential curve and straighten it out, allowing us to find a reliable, constant slope. Recognizing the exponential, curved nature of first-order clearance is the prerequisite to applying the correct formula on the NAPLEX. That mathematical tool is the natural logarithm, denoted as ln. It is the mechanism required to linearize exponential decay. Taking the natural log of the concentrations transforms proportional, fractional decreases into clean, additive changes that we can actually measure with a straight line. Changing the y-axis to the natural log snaps the exponential curve into a straight downward line. Applying standard slope gives ln of C1 minus ln of C2 over elapsed time. Algebraically, this simplifies into our target equation: Ke equals the natural log of their ratio divided by time. The Ke equation is not arbitrary. It is simply the linear slope of a logarithmically transformed reality. Let's execute this mathematical framework using the clinical parameters from our hospitalized patient. First, we identify the variables for our numerator. Our starting concentration, C1, is 8 milligrams per liter. Our second concentration, C2, is 2 milligrams per liter. We substitute these values into the numerator, taking the natural log of 8 divided by 2, which simplifies to the natural log of 4. Next, we identify the time variables for the denominator. T2 is our 6-hour draw, and T1 is our 1-hour draw. We calculate the total elapsed time by subtracting 1 from 6, giving us a denominator of 5 hours. Returning to the numerator, the natural log of 4 is approximately 1.386. We complete the final division. 1.386 divided by 5 hours yields an elimination rate constant of 0.2772. This single number, 0.2772, perfectly models the exact exponential decay curve happening right now in the patient's bloodstream. In pharmacokinetic calculations, tracking your units is just as important as the arithmetic. Because the numerator is a ratio of identical units, milligrams per liter divided by milligrams per liter, they cancel out. The numerator becomes unitless, leaving only hours in the denominator, written as inverse hours, or h-1. An inverse hour has a specific practical meaning. It tells us the exact fraction of the remaining drug that is eliminated from the body every single hour. The NAPLEX prompt requires strict precision, asking us to round the answer to exactly 3 decimal places. We round 0.2772 to 0.277, truncating the final digit. This locks in our final answer for the clinical scenario, an elimination rate constant of 0.277 inverse hours. Remember this rule for first-order kinetics. Never subtract concentrations directly. Always take the natural log of their ratio and divide by the elapsed time. Mastering the difference between linear subtraction and logarithmic ratios ensures both accuracy on the exam and safety at the bedside.